Well, hello everybody. Kind of a weird situation, but here we are. All right, we just need to jump in, finish out this semester. All right, you might want to pause the video and go look for this worksheet, these notes that we did that Friday before spring break. You can see up here I titled it second, and this was March 6th, that Friday before spring break. We didn't complete it, and I just mentioned that we would complete it the first day when we get back. Well, this is the first day we get back. All right, just a review, because in case you've forgotten, well, I know I have. The content here is about sequences and series. So if you've forgotten what a sequence is, we have the information here. If you've forgotten what a series is, it's here. All right, if you've forgotten what finding the sequence of partial sums means, then it's here, all in our work. We did talk about divergent and convergent. And we'll return to talking about that today too. When we look at these five partial sums right here and we put them in a list, a sequence, if you look at each one of these values right here and change it to a value on your calculator, it doesn't appear that the next number would be approaching some particular number. It just appears that the next number and the next number in the sequence, those particular partial sums, is actually getting bigger and bigger. We started at 1, we're at 1.5, 1.75, a number a little less than 2, but then in this last term we get a number that's a little bit bigger than 2. So there's no suggestion here with this sequence of partial sums that we have a limiting value. So we say that this series probably is going to diverge, increase without bound. Okay, it goes to infinity. Example 2, we found the first 5 partial sums. And it appeared as we looked at each of these values right here that it almost looks like the next number and the next number might be leveling off to a sum of 1, or the next number, the sums might be leveling off to a half. So because this is not infinity and it's a number, we would probably have a discussion about this series possibly converging. Okay, on the back, to remind yourselves, we looked at geometric series and what those look like. Here's the structure. We looked at convergent and divergent geometric series. A geometric series is a series that's created by always multiplying by the same number to produce the next term in that series. If we do have a common ratio, or that number that we're multiplying by, that it has a value, an absolute value that's a number between 0 and 1, less than 1, greater than 0, then we say that that sum of that series is going to converge, and the sum can be found by using this sum formula where a is the first term divided by 1 minus the common ratio. So we looked at 4 examples down here of geometric series, and I think what we did is we took the series in sigma notation and we generated a few terms just to get an idea of what those terms' behavior would be, to see if we can kind of see what the common ratio is, identify the common ratio. Once we see that the common ratio's absolute value is less than 1, we know this is a convergent geometric series, and we can find the sum. If we were to take and add every single one of these terms, an infinite number of them, the sum would level off to 6. Same thing here, we generated a few terms, and then what we saw was the common ratio was 5/4, that number being bigger than 1. So that just tells us that each individual term, as you proceed through this series, is getting larger and larger. And if you go back and you add all those together, well, that sum is just going to increase without bound. So there's no limiting value, so that sum diverges. Here, it looks like we didn't generate a few terms here. It looks like it. But we did identify the common ratio to be a number 3/2 bigger than 1, so we knew right then that geometric series would diverge. Last example, it is geometric in nature. We did not generate a few terms here, but had we done that, we would have seen the common ratio to be -1/3, and the absolute value of that is a number less than 1. So if you were to generate an infinite number of terms and sum them, the sum would equal this value right here. The first term, a, so when n is 0, because it tells us n is 0, the first term is 2, and when we go to the formula, 1 minus the common ratio, even if it's negative, we use negative, we get 4/3, and we did the math, and we got 3/2. Okay. So this is where we left off. We didn't have time. We're going to look at properties of infinite series. Okay, you can always reference your textbook because I have the pages here. All right, theorem 9.8 talks about the limit of the nth term of a convergent series. So if we think about convergent series that do have a sum, okay, some of the things we want to record is this. Okay, if the series created by the sigma notation converges, as we saw a couple of them did right here, okay, then it has to be true that the limit as n goes to infinity, the number of terms goes to infinity, of a sub n, those terms, is approaching 0. So if we have a convergent geometric series like we did up here, then it has to be that when we take a peek at later and later and later terms in that series, it appears that those terms are approaching a value of 0. Well, let's find one where that happened and we had generated the term, like this one. This was a convergent geometric series. So I see this is 3, this is 3/2, already less than 3. This is going to be 3/4, 0.75. This is 3/8. This is going to be 3 over infinity eventually. Well, 3 over infinity is 0. So the further you go out in this series, the limit of the nth term, this number has to be approaching 0 if this is a convergent series. See, what other one was convergent? Oh, this one. We didn't generate any terms, but if we did, starting when n was 0, generated some terms, we're going to see that each of these terms are getting closer to 0. Sometimes the terms are positive, sometimes they're negative, because the terms of this series alternate. But it doesn't matter. They're still getting smaller in value, closer to 0, whether they're closer to 0 from the positive side or the negative side. So it has to be true that if we have a convergent series, that the limit of the nth term has to go to 0. Because you don't want to keep adding numbers, in that series that aren't 0 if you want a convergent series. All right, furthermore, it says if a series converges, the limit of its nth term must be 0. That's this statement. Okay, some things to think about, what this is not saying. If the limit does go to 0, no mention of convergent or divergent, okay, then that series may or may not converge. So the converse is not true. Just because I look at a series and I see the later terms are going to 0, I don't know what happened before those later terms. This may or may not converge. Furthermore, if the limit as n goes to infinity of the nth term does not equal 0, maybe the limit of the nth term goes to 2, goes to 2, goes to 2. Well, that just means you're adding 2, adding 2, adding 2, and your sum isn't going to level off when you go back to add all those together. So this is the important part for us, the takeaway. If the limit of the nth term does not equal 0, then the series has to diverge. So from that, we come up with theorem 9.9. We have a test for divergence. Not convergence, but this is a test. The nth term test is for divergence. So it says that the limit as n goes to infinity does not equal 0, then that means that the infinite series has to diverge. So let's see how in examples this theorem can be put into place. All right, the directions say let's use the nth term test for divergence, okay, not convergence, to determine if the series diverges, or let's see if the nth term test is inconclusive. So far we've got all these problems splattered on our paper, and we could generate, a bunch of terms and look at the individual terms to kind of analyze to see if we feel like, oh, I think that, this series might be converging. Or maybe this series, no, it's not converging, it's diverging. Okay, that'd be a lot of work to generate a bunch of terms. So let's use the nth term test for divergence to see if any of these series diverge. Okay, all right, for example A. So our work is going to involve us finding a limit. So let's find the limit as n goes to infinity of the nth term. Well, the nth term formula is 2 to the n. All right, now if you want to generate a few terms to see what happens, well, certainly you can do that. That would be 2 to the 0 plus 2 to the first plus 2 squared, plus you're going to add 2 cubed, then you're going to add 2 to the fourth plus ... plus 2 to the n plus, it's an infinite series because we go to infinity. Well, you go back and you add all those up, you're not leveling off to any particular number. This sum is increasing without bound. So what's the limit as n goes to infinity of 2 to the n? Well, I don't know, but it's huge. I'm going to call it infinity. So right here, we know that each individual term is getting bigger and bigger. Infinity is not equal to 0. So right here, we know that this series is going to diverge. So I'm going to do stack of 3 dots. Therefore, I'm going to put down here, this series diverges by the nth term test for divergence. So this test, okay, just involves our finding out whether or not this series diverges. Okay, before we move on to another example, it's probably worth looking at this series again. You might notice that, hey, this was a geometric series where the common ratio is 2. Well, think about what we already know about geometric series and the common ratio. Because this common ratio is a value greater than 1, that geometric series situation tells us that because this R value is greater than 1, we immediately know that this geometric series diverges. I'd never be using the little sum formula for a geometric series of first term divided by 1 minus common ratio because this series diverges. So actually there's a couple of tests that we could use for convergence and divergence on this particular series because this series is geometric. And I might want to go with that first and go, wait, common ratio greater than 1, series diverges, I'm out. Likewise, another test that could be used that tells us the same answer, gives us the same result, is the limit of the nth term goes to infinity. Therefore, by the nth term test for divergence, this series has to diverge because it's not equal to 0. Let's look at another geometric series. So let's look at D. You could generate a few terms, but this is a geometric series, but I'm told that I want to use the nth term test for divergence. So I'm going to set up the limit as n goes to infinity of the nth term. Now, if you're not sure what's happening here, you could generate a few terms and take a peek in at those terms, but as n goes to infinity, the numerator stays 1 or negative 1, but the denominator goes to infinity. Think about applying the n here and the n down here. This is going to 0, multiplied by 0. The limit of the nth term equals 0. This is what we call inconclusive because it's equal to 0. Okay, this may or may not converge. So, but by the nth term test, I'm going to put therefore, because I got 0, the nth term test is inconclusive. I don't know if this series converges or diverges. All I can say at this point is the nth term test didn't tell me anything because I got 0. If I'm using the nth term test, finding the limit of the nth term, I need to get a number that's not 0 so I can respond and say, oh, that series is divergent. But if you end up with 0, we don't know. However, what else do we know? We know that this is geometric. Generate a few terms, figure out what the common ratio is. The common ratio is actually going to be negative 1/3, the absolute value of which is less than 1. So I know because of this structure that this is a convergent geometric series because of my earlier work. But the directions again just said for us to use the nth term test for divergence or state that the nth term test is inconclusive. And it is, that test is inconclusive here, although we do know a bit more about this particular series and it being geometric and that it does converge. But that's not what they want me to respond to. Okay. All right, let's skip around a little bit. Let's look at C. If I'm using the nth term test for divergence, according to the directions of what I'm supposed to do, I've got to find the limit as n goes to infinity, that's an arrow, of 1 over n. Let's kind of evaluate. If n goes to infinity, 1 divided by infinity is very small. It's 0. Do I know if this series converges or diverges? Nope. I can't say either way. All I know is that this series, or that this is an inconclusive test. So the nth term test is inconclusive. And we're done. We might as well leave it. If you wanted to expand, you could put n as 1 and get 1, plus, if you want to let n be 2, I'd get 1/2, plus a third, plus a fourth, plus a fifth, dot, 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 plus 1 over n, plus, dot, 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 and it goes on. It looks like this should converge, but actually I know a little bit more about this through other calculus work, and this actually does diverge. But we would need another test, and we're not going to study that test. All right, let's look down here at E. You could generate a few terms, letting n be 1, then 2, 3. Take a peek in at the individual terms of that series. Okay. Otherwise, let's find the limit as n goes to infinity. All right, I'm going to take us back to algebra and n behavior. What if I changed n to x, and this n to x, and this n to x right here? This is n behavior where we compare the degrees of the exponents. So think of these being x's instead of n's. Think of these exponents being understood to be 1. So what's the limit as n goes to infinity? Well, when the exponents are the same in a rational function, then we know that we have a horizontal asymptote at the coefficients, the numbers in front of those powers, those terms. So this is actually equal to 1/3. You can kind of analyze it too. We have an infinity over 3 times infinity plus 2. This plus 2 is negligent. So what's an infinity divided by 3 infinities? Well, that ratio would be 1/3. All right. 1/3 does not equal 0. Therefore, we can say that this series diverges by the nth term test. So what are we looking for? We're looking for not 0, so we can say that the series diverges. What this means is that all the terms in this series, when you generate a few, they're approaching 1/3. The next one's approaching 1/3, then you're going to add another third, then another third. If you keep adding thirds, you're not leveling off. Your sum is shooting up there to increasing without bound to infinity. So that series is said to diverge. And we saw that and proved that it diverges by the nth term test for divergence, because we did not get 0 when we found the limit of the nth term. Let's look at F. Same idea here. Think of all the n's being x's. Look at the exponents. They're the same. When the exponents are the same, we take the ratio of the coefficients. So this limit is actually going to be 1. Well, does 1 equal 0? Nope. So what do we know about this series if we were to generate a bunch of terms and then keep summing them? Well, since the nth term is going to go to 1, 1, 1, 1, 1, and you keep adding all those ones, the series is said to diverge. All right, how about we try G? Think of this as a rational function. If we change all n's to x's, same exponents. This limit's going to go to 5/3, which is not 0. So the series is said to diverge. Okay, and let's jump down to I. It's a similar problem. We're using the nth term test for divergence, so we find the limit of the nth term. The rational function, if we change all n's to x's, same degrees, ratio of the coefficients, 1/3. We don't look at these other terms because the most impact on these answers, numerical values, will come from the higher exponents. So this series, if you were to generate a bunch of terms based on this formula, here would be said to be to diverge. Okay, hopefully you feel comfortable with those. Now let's look at H. It's an exponential fraction that's been made into a fraction. So what we've been doing here in these last few examples really won't apply too much just yet. So let's see what we can do. I could generate a few terms if I want, but let's see if we can analyze what's happening mathematically. Okay, if I were to plug in infinity, I'm going to need infinity here, infinity plus 1 here, and this -2 really has nothing to do with what's going to happen later out in the series. This is how we handle this one. Rewrite the limit. Rewrite the numerator. Notice this -2 is not with the exponent, but right down here, what I'm going to do is I'm going to break that apart. I want to have a 3 to the n in the bottom to match the 3 to the n in the top. I don't want a 3n plus 1 in the bottom. So I'm actually going to take the denominator and say, you know what? This really is 3 to the n times 3 to the first. Thinking about properties of exponents, if you were to multiply these two factors with the same base, I would just add the two exponents, and that would result in this format right here. Well, it's good to kind of break up that exponent and make that a 3 here, because what I can do is I can think about pulling out a 1/3 and putting it in front of my whole limit statement. Where'd I get the 1/3 from? From here, and a 1 on top I can pull out. So that leaves 3 to the n minus 2 over 3 to the n. So you really want to try and get the same exponents here. So I've got 1/3 times, and I need a number to go in here that's going to result from my evaluating that. Well, if n goes to infinity, this -2 isn't really going to have anything to do with my answer. So think about 3 to the n over 3 to the n, which just divides out to 1. This limit is actually just going to 1. So my answer is 1/3, which does not equal 0. So this series is said to diverge. Therefore, series diverges. And I'm going to do ... running out of time and space. Okay, diverges by the nth term test for divergence. You might notice that we have two problems left, and they both involve factorials. I think we've talked a little bit about factorials, but if we haven't, no, I'm pretty sure we have, but let me just give you a quick example. I think I even showed you on your calculator where you might find the factorial key. If I knew what n's value was, like 7 factorial means start with 7 and then multiply by one less integer until you get to 1. So times ... 3, 2, 1, and you'll get a value. All right, problem B. You can generate a few terms, inspect each term, analyze each term to see is Are those terms going to zero? Are they getting bigger? Notice down here, this is 2 times n factorial. You can think of this like the rational expressions by comparing the exponents that we just saw. These factorials kind of behave that way, at least in this case with this problem. Okay, you can think about this having a coefficient of 1 in front here. And as n gets larger and larger, and this value gets larger and larger, that plus 1 is irrelevant. This limit is actually equal to 1/2, which does not equal 0, and the series diverges by the nth term test for divergence. Running out of space and time. Oh, but let's compare now this example B that we just did with J and how it looks different. Notice that the factorial falls after we have a sum. We want to try and get the same factorial. Well, what number is bigger, n plus 2 or n? Well, n plus 2 is the bigger number. I'm going to come back, I'm getting ready, but I'm going to come up here and I'm going to say that this is actually equal to the sum of n equals 1 to infinity. Since n plus 2 is bigger, I'm going to start there. I'm going to keep the n factorial down here. Well, I'm going to detach the factorial and say, okay, the first number would be n plus 2, whatever that is. 1 less than this number would be n plus 1. All right, I'm going to keep going generating the factors until I match exactly the smaller number here. Well, what's 1 smaller than n plus 1? Well, that would be n. Reattach the factorial, because now what we can do is we can think about dividing these two factorials out, and we're left with just evaluating n plus 2 times quantity n plus 1, and I really don't need a fraction here. Okay, well, this is really a simplified version of this term right here. So when you plug in infinity and infinity here and you multiply them, this is going to go to infinity. Those terms, each individual term will go to infinity, not 0. So we can say that the series diverges by ... the nth term test for divergence. So hope that helps.